Its title is W star bundles and continuous families of subfactors.
Thank you, George, for the introduction, and thank you to the organisers for giving me the opportunity to speak to you today at this wonderful institution. Okay, so we've had 3 talks so far today on C-star algebras. My talk is going to be a hybrid of C-star and W-star theory. The key objects are W-star bundles. So loosely speaking, W-star bundles, well, they're bundles, so there's going to be a topological space here. And each fibre is going to be a von Neumann algebra, and in fact a von Neumann algebra with a canonical trace. So at the fibre level there's von Neumann algebra theory, but when we're interested in fibres that are near each other, so correspond to points in the base space that are close to each other, there's going to be continuity conditions between these two, and in fact they're going to be continuity conditions with respect to 2 norm, and so that's where sort of C-star or topological star behaviour enters the fray. The motivation for these W-star bundles were introduced by Ozawa in 2014. The motivation was related to this Toms-Winter Conjecture, which has been mentioned a couple of times today. So this is to do with the class of C-star algebras which are accessible to classification by K-theory and traces. I'll say a bit more about that in the second part of my talk. So results about W-star bundles have real applications to this important conjecture in C-star algebra theory. And in the final section of the talk, I want to talk about continuous families of subfactors. So in the process of studying W-star bundles, I realised that that you can use this as a framework for studying certain continuous families of subfactors. I come up with some examples which I'll show you today, and I'm really interested in if anyone has ideas for naturally occurring examples where you have subfactors and there's some sort of parameter and you expect there may be some sort of continuous dependency that will often give rise to an example of a sub W-star bundle in the framework that I'm going to introduce today. And so this looks like a really interesting area of research going forward. But let's begin with some definitions and examples. The definition of a W-star bundle may look strange first, but examples will clear things up quite quickly. So this is a definition due to Ozawa 2014. Okay, so a W-star bundle, I tend to use script letters for W-star, so script M over the compact Hausdorff space, generally written X, is a unital C-star algebra and so the continuous functions of X are embedded in the centre of this C-star algebra. So this is a unital embedding. And not only have that, with that, and a conditional expectation and this is written E. It goes from the C-star algebra down onto this subalgebra C of X, and then we have some axioms such that, slow that up, and so the 3 axioms. First one is a tracial condition, so we want this conditional expectation to behave like a trace. This is for all B and A in M. Then we want a faithfulness condition, so if E of A star A is 0, this forces A to be 0. And the final condition is the one that looks a bit strange at first. What we require is that the unit ball, so what I mean by this is things of norm at most 1. This is complete in the norm, and this is what we call uniform 2 norm. It's defined very much like the trace 2 norm on a 2-1 factor. You take E of A star A, square root it, and then we take the subnorm in Civ X here.
Question?
Yes?
What does this definition restrict to when all the algebras inside are abelian?
When all the algebras are abelian? That's a good question for abelian. I'll show you what some other. I'll think about that, and I'll show you the 1 point case. This is actually really good for getting some sort of orientation on this theorem. So this is example 1. X is a 1 point space. So when X is a 1 point space, you can do lots of identifications. So continuous functions on the 1 point space here will give rise to, this is just identified with the complex numbers, which in turn gets identified with the centre of our algebra M. So there really is nothing going on with the embedding. And what you find is that this E, the conditional expectation, is nothing more than some state on the C-star algebra.
Trace, I would say.
Okay, so it's states up there, but this is now going to be a trace. So, yep, T and F force this thing to be a faithful trace. And this is where axiom C comes into play. So axiom C is precisely the condition that we need to ensure that when we take the GNS representation and the image of M under this, we actually get a von Neumann algebra. So you can view this completeness in the of the unit ball and the C-star norm with respect to the 2 norm as a abstract way of formulating von Neumann conditions here. So that's the first example. Second example, these are trivial bundles. So what we do here is where we, so X is any compact Hausdorff space, and M Tor is what I call a tracial von Neumann algebra, TVNA. What I mean by this is a von Neumann algebra plus a faithful full normal trace. Okay, yeah, so this condition also gives you the normality of phi here. Of phi, because it's going to be given by a vector state on this GNS representation.
I suppose you could take the center value trace.
Yep. So in this case, we've got this setup, and we define M to be generally noted C sigma X M, and this is the functions from X into our tracial von Neumann algebra, and we require that they're bounded with respect to the C-star norm, and they're continuous. So continuous with respect to the 2 norm for the trace. So the boundedness condition here is necessary because if you for this to be closed under multiplication, because the estimates involving products, if you take the 2 norm of a product, you can only bound this by 2 norm of one part and the C-star norm of the other part. Okay.
Well, I guess if you just took if you take a phenomena, a finite phenomenon algebra, and then look at the center value trace, then that wouldn't be trivial, but it would be one of these, I guess, with the C of X being the center.
It's close, but of course, the center might not be C of X for the finite von Neumann algebra. It'll be some meta-theoretic. Okay. So if you're having some
anything is C of X for some X, yeah.
Okay.
And it's not continuous.
That's the problem.
Yeah.
Not continuous.
Okay. So
yeah, but that's not one of the axioms, is it?
I think the finite on the if you allow example 3 to turn up, there's a good chance you'll see the finite part of the bijury.
Yeah, that's true as well. So leave this for the moment and move on. Example 2, this is a trivial bundle here. One thing you note from this example, if it wasn't clear already, is that although we use the terminology W star bundle, this is very much in the sense of functional analysis. So we're really studying sections of a bundle from so if you're an algebraic topologist and heard about bundles, then we're really studying the algebra of sections of a bundle. There is a total space picture here for those who have studied these things before. Okay, so that's trivial bundles, that's example 2, and I wanted to quickly go forward a bit to say a bit about subtrivial bundles. An easy way to get new examples from here is just to restrict in certain coordinates. So if you have a family of sub-Neumann algebras nx parameterized by a base space x of M, you can of course restrict the things in here that have f of x to be in there. Okay, we'll come back to this example in much more detail. Of course, if I just use any family of subalgebras n of x, then I have no real right to expect that I can actually construct something that has continuous and actually takes the value in each nx for each x, because, well, it could, if they were very different at nearby fibers, then there wouldn't be possible to connect elements in those two subalgebras. But I'll come back onto this example a bit later. Now to the example that George was mentioning a bit earlier. Where should I put this? I'll put this on the first one. Very closely related to what George was mentioning earlier. So this is strict closures of C-star algebras. Closures of C-star algebras. So this is also due to Ozawa. So how does this work? So you're given A, which is going to be, let's say it's a simple separable C-star algebra. Simplicity isn't required for all of this with compact extreme boundary. And we can, given this data, we can produce a W star bundle called A strict closure over X. And the idea behind this construction is going to be that we are going to complete the unit ball of A with respect to a uniform 2 norm, because we can define uniform 2 norm just at the level of the C-star algebra. We take the supremum over all tracial states of A of the trace of A star A to the half. But this is sort of an incomplete description here, because although I've sort of made this axiom C true by definition, it's not at all clear where the embedding of C of x inside this algebra is actually going to come from. So, for example, if I have a simple C star,
Completing where function algebra?
complete the unit ball.
Just like abstractly, because then you have to know that the multiplication.
Okay, so you can actually do this. So there's the standard way you complete things in functional analysis, where you take L infinity. Well, so you take the product space and then quotient out by take Cauchy sequence and quotient it by null sequences. You can do exactly the same thing, but take bounded Cauchy sequences and quotient out. So yeah, so that's something that is an issue, but I'll sweep that to a side. So what I wanted to say is that here is the way you get at this properly is to use the finite part of the Vigil, which links back to what George was saying. So given A, we can study the Vigil. So this is the von Neumann algebra, and we restrict to the finite part of the Vigil. So right, this is N. So this is a huge von Neumann algebra, and containing, it will contain A. That's why I said simplicity there, just to make sure that A was actually properly included in here. Now, this example here, this will have a large centre, and it has a centre value trace. What you can show is that C of X really does sit inside this. So this is this non-commutative Radon-Nikodym theorem to show that you really can produce elements in the centre of the finite part of the Vigil with prescribed tracial behaviour. And the key part of Ozawa's work was to show that you don't need to pass the whole finite part of the Vigil. You can actually pass to something slightly smaller, which is still big enough to contain, it's still big enough to contain all the continuous functions. This is the tricky bit to prove. So this is similar to what George was saying. If you take this example here, so this of course will be C of X for some X, but it will be C of X for a much larger X than the finite part of the boundary. Particularly it will be usually non-separable set. So this is the example that's sort of key for the applications to C-star theory. But I've talked about bundles a lot and given you a few examples, but I haven't really talked about fibres. So it's a bundle, it has to have fibres, so I really should tell you what they are and what they are in the examples. So let's do this briefly. So how do we get fibres? Fibres. So the setup is that M is a W-star bundle over X, and we're taking a point X in X. So how do we get the fibre? Well, there are a few ways to define this. My favourite is you quotient out here by the set of things that when you take their well, this sort of conditional expectation of A star A, it vanishes at the point. So it's the things that are sort of trivial at X. There's a bit of notation here. I tend to use functional notation to describe the passage from a bundle to its quotient. This is not just, this is obviously going to be a C-star algebra. Well, not entirely obvious, you have to show that this thing really is ideal, but that's elementary. But it's not just a C-star algebra, it really has a trace, so we can define a trace by this formula here. Proof that this is well defined is just an application of Cauchy-Schwarz, it's not too difficult. And the real theorem, this is due to Ozawa, is that in fact this pair is a tracial von Neumann algebra. So what this means is, well, either it means that the unit ball here is complete, of this C-star algebra is complete in the relevant 2 norm, or of course it could also equivalently be said to saying that if you take the GNS representation of this C-star algebra with respect to this trace, then the image of that is a von Neumann algebra in the represented version of the definition. That's what fibers look like. And in particular examples, fibers are quite easy to pick out. So if you have the trivial bundle, C of x m, and you specify a point in there, in x, the fiber is isomorphic to just m, and via evaluation. So passing to the fiber is actually the same thing as just asking what value does the function take at a particular point. In the subtrivial example over there, so subtrivial example, you can ask what the fiber is. Well, it's isomorphic to what you get when you evaluate this algebra at the points of the things that you can get at x, which is always a subset of the data you specified in the definition, but not always equal to it. And in the important example that I mentioned before, so in the C star case, so when M is the strict closure of a C star algebra A, with the conditions stated there, to recall that X are extreme traces. So what happens in this example is that the fiber at a certain trace is actually isomorphic in a very natural way to not M, to taking the closure of the GNRS representation of A with respect to that specific trace. So in a lot of cases that are of importance to the classification program, this is going to be R. So for example, when A is simple, separable, nuclear, unital, probably infinite dimensional as well, just to. So these examples come from C star algebras. You get a lot of W star bundles where all fibers are isomorphic to the hyperfinite 2-1 factor. And this sort of brings me quite nicely into the section 2 on this trivialization problem. Okay, so trivialization. So the key question here is, given a W star bundle M over X with all fibers isomorphic to the hyperfinite 2-1 factor, is M as a whole isomorphic to this trivial bundle as W star bundle. So I mean not just isomorphic as C star algebras, but the appropriate commutative diagrams involving the expositional expectation and the embedding of C of X is also preserved by this isomorphism. So this is actually quite an important question, and it's good to think about what implications this has. So implications of triviality. So implications of triviality. So if you've got a trivial bundle, this implies the existence of projections. So this is a really good example to show the sort of interplaying nature between C star theory and W star theory. So at the level of fibers, these are von Neumann algebras, so you can definitely find projections at each fiber. You can lift them, but of course you can't always lift projections to a projection. So you can take the lift nonetheless, and it'll be approximately a projection in a two-norm sense at all fibers nearby. But actually gluing these together to get something that even behaves approximately like a projection globally is very difficult. The issue, of course, here is that if projections don't commute, then adding them gives you something that's nothing like a projection. So, existence of projections, and more generally,
Even if they commute.
even if they commute? Yeah. Okay, so more generally, Valley embeddings of matrix algebras into a subbundle. So all these things that we sort of take for granted in the world of von Neumann algebras, trying to prove these for a general W subbundle is very difficult. If you go to get these, you have to go via a trivialization result. And these are very important in what I'm going to call converse directions. Directions of Toms-Winter. So this is the statements that finite nuclear dimension, this property that Stuart mentioned in his talk and came up also in Wilhelm's talk, proving that this is equivalent to conditions like Z stability and like strict comparison, so like the von Neumann property. Oh, you saying something? So like the von Neumann condition that comparison of projections is determined by traces, going one direction is actually very easy. So, well, not very easy, but done, and done in general. So going from, for example, finite nuclear dimension to Z stability is known in general. This is a result of Wilhelm. Going back, however, is a difficult result, and this requires heavily some of the results on triviality of bundles. So what's known about the triviality problem? The first most important thing to say is that there's no known counterexamples. But positive results, a few are known. So triviality is known when the base space, the covering dimension of the base space, is finite, and that's, I suppose, a technical condition where that says M is strictly separable. So this is equivalent to separability in uniform two-norm, sort of needed for an inductive argument here. So this is a result of Ozawa.
Why does X have to be compact? It's all, after all, it's always a topological space, a Polish space.
Let's have a think about that for a moment. Why does it have to be compact? So I think you probably, so in terms of the abstract definition of a W star bundle, you can probably generalize it to locally compact because you want to say in this, to deal with non-neutral C-star algebras. But the real answer to that question is that this example, these strict closures of C-star algebras, to get the argument of Ozawa to work, you really do want the compact extreme boundary there. Otherwise, you don't get this any C of X lying in the center of your strict closure.
Well, I don't know. I don't see that as a difficulty. The difficulty I see is like, see, if the extreme points are dense, then there aren't any continuous ones. I mean, it would certainly be in the.
Yeah. So the issue is that you could give a generalization of the definition of the W star bundle, but it won't be the one that's relevant for the purpose of the Toms-Winter conjecture. So you'd want to give a different start with a different definition, and there is actually work going on in this direction. But I'm not talking about it today.
Reality wouldn't solve the problem.
So working at Toms-Winter outside this compact extreme boundary, you need new techniques. That's definitely true. Okay, so positive results. There's that. Also, it's also known that if you take W star bundles coming from Z stable C-star algebras, this also implies triviality. So there's another example there. And final one, this is essentially due to Ozawa as well, made explicit in the 6th author paper BBSTWW. And the third one condition here is when M is locally trivial. And this is a result of myself and Ulrich Pennig, who's based in Cardiff now. So local triviality, what does that mean for a W star bundle? Let's tell you that briefly. Best way to explain it in terms of what I've already defined so far is to talk about total space construction. So people who've seen either continuous fields of Hilbert spaces, continuous C of X algebras, those things will recognize this as quite a familiar construction. So what I can do, if I have a W star bundle over the space X, what I can do is I can take the fibers MX, I can take their disjoint union as a set, and I can also endow this with a topology, which I won't describe now, but the point is that such that M becomes the algebra of bounded continuous sections. So the point, this is obviously a bundle in the more topological sense, because you just take a point here to its which fiber it comes from. So this gives you a description of a general W star bundle that's much more like the trivial bundle. So then instead of having them as functions that are bounded with respect to the one norm and continuous with respect to the two norm, you now have sections of a bundle that are bounded point-wise. Each of these is a C-star algebra, so there's a norm on each of those, and continuous in the sense of this topology here. And in this case, when you have local triviality of, well, this space here, local triviality, so locally trivial W star bundles, and turn out to be in one-to-one correspondence with what are called principal ought. Okay, I'm going to say M bundles. So for this thing to work, I should say here that all fibers here are isomorphic to the same thing, M. And these things are well studied by topologists, and what the crucial bit of information here is that actually the automorphism group of R, although it's big, is actually contractible in the U topology. So this is a topology defined by norm on the pre-dual. It's actually equivalent to most sensible topologies. So point-wise, two-norm convergence gives you the same topology as the U topology here, but it's contractible here. And so what this means is that none of the clever topological tricks that can produce some sort of non-trivial bundle, none of them will work. You get all bundles over, all locally trivial W star bundles are trivial, which is this result here. So that's my brief introduction to how triviality and the trivialization problem of W star bundles. Now, in the last 20 minutes, I want to talk a bit about this continuous families of subfactors, which
I think you do actually have 20 minutes.
20 minutes. Oh, okay.
much time you want to allow for questions.
Well, I'll say what I want to say and then we'll have some questions. Okay. So, continuous families of subfactors. So this is me going back to the subtrivial bundles that I put up there. So let's say back to subtrivial bundles. Okay, so set up. So X is compact Hausdorff. M Tor is a tracial von Neumann algebra. And then we have a family of sub von Neumann algebras of M. So this is the setup, and the M was the trivial bundle, and N things for work. So there are two questions you might ask in this setup. First question. Question 1 is, so we know that the fibre here is isomorphic to the values that we can get when we evaluate functions in N at the point X, and that it's less than the data we're given. When do we actually get equality? When do we have equality? And a related question, question 2, is when is there a say E preserving conditional expectation going from a W star bundle down onto N. So these questions actually have quite clean answers. Answers. So they're both in terms of continuity, and the appropriate measure of continuity here is distance function. So I mean distance between A and NX is going to be this infimum of 2-norm distance in 2-norm, and of course this thing is actually realized by conditional expectation. And so the answer to question 1, this is equivalent to upper semi-continuity of the map so looking at what the distance between a fixed A in our algebra and this varying family of subfactors is. This requires upper semi-continuity, and it's essentially a petition of unity argument to show that if you have an element in a certain element of Nx, you really can build an element, continuous function that has this value at the point. Answer to the second question, this turns out to be equivalent to continuity of this function for all a in M. Okay, so that's a lot of general theory. Let's have a look at some actual examples of this. So, first example I wanted to show you is what I call dimension drops. Because it looks very familiar to other things that go by this name. So here I just take my family nx to be the whole thing everywhere except a point and something else at that point. So some other von Neumann algebra, and what you find is that 1 has a positive answer but 2 has a negative answer. So what you do get is you get a W star bundle, a sub W star bundle of this trivial bundle, and it has the right fibers, the ones you prescribe, but there really is no conditional expectation here. So this fact that all sub algebras of a finite von Neumann algebra have a conditional expectation, a unique trace preserving conditional expectation, this can fail in the context of W star bundles. The other example, which I think is perhaps even more interesting, is this one here. So what happens in this case? So here I have a specific base space in mind. I have the simplest possible one where something could go wrong. So here's the natural numbers plus infinity, so 1 point compactification of n, and so my fibre is going to be the hyperfinite T1 factor, but it's convenient to write it as in fact the infinite tensor product of R's, and we're going to want to have the automorphisms here, which flips the ith and I plus 1th tensor factors. And the interesting thing about this example is that when we define n, well, okay, so I've used i's rather than x's, so when we define ni to be the fixed point subalgebra of this map here for I a natural number, and then we define it to be the whole thing for I equals to infinity, what you find out in this case is that the answer to both questions is actually positive. So 1 is yes, 2 is yes. So we really do have a sub W star bundle, and we do have a conditional expectation going onto it. The way you see this is that any element fixed of here, you can approximate it by something that's just 1 after in all tensor places close enough to infinity. And so it will be very close to lying in things in these subalgebras for large I. But what's interesting about this example is that you have a discontinuity appearing in the index. So I'll just write it as n, so mi over ni is equal to 2 for I natural number, but it's only equal to 1 when I is infinity. So this is either there could be, although we're studying continuous family of subfactors, discontinuities can arise in the index. Okay, so that's my 2 examples that I want to show you. Now, just a hint about the general theory that's behind these. So for convenience for this talk, I've focused on subbundles of a trivial bundle. So the larger W star bundle has always been well, these C sigma of xm, but you can still do it in more general framework. So W star bundles. Here's the general framework where you have C of x inclusions of W star bundles. So what I mean here is that M is the W star bundle over X, the conditional expectation E from M to C of X, and then N is also the same thing, and the conditional expectation is just the restriction. So it gives you a bit more freedom to define things. It's not hard to prove in this context that for all points in the space, when you restrict to fibers, you really do get a trace-preserving inclusion of finite von Neumann algebras, and their equivalent generalizations of both the questions 1 and 2 and their answers. In this context, so you can, given a general M and some prescribed data for the ends, you can decide whether there is a subbundle and whether it has an expectation. The other thing you can do in this framework is you can do a basic construction. So assume that N inside M is a sub W star bundles, and there's an expectation En. So question 2 has a positive answer. Then you can look at you can study the basic construction in this context. So what this means is that we represent N and M on this L2 space. Of course, we're working with W star bundles, not with von Neumann algebras, so this thing is a Hilbert C of X module. But nevertheless, formally you can define it in very much the same way as you do standard form for a 2-1 factor, say. So we're representing these things by left multiplication. There is a J operator that intertwines left actions and right actions, for example. And we can also show that the conditional expectation En extends to an adjointable map L2, and what I was thinking here is projection. And then in the same way you do for finite von Neumann algebras, you can consider the algebra generated by these things. So this would be the, let's say, strictly closed start of algebra, and it's of the adjointable operators, so L of L2 of M. So very much like in the case of finite von Neumann algebras, but you have this difference that we're working with Hilbert C of X modules and adjointable operators rather than Hilbert spaces and their bounded linear operators. This makes things much more difficult because notoriously projections are hard to find in this space. Nevertheless, you can actually push a lot of ideas through. The algebra of standard form works exactly the same way, with exactly the same proofs. When you start doing analytical properties, you do have to use different proofs now. The most important example of this will be a double commutant theorem, which is very important. For example, you want to prove things like you want to identify this with J of the N commutant J. and things like this. These are very important results in the subfactor theory. So how do you do this? Well, these work by a fiber-wise argument. So the point here, I'll just explain this in words rather than giving some details here, is that Hilbert C of X modules naturally have a fibration into Hilbert spaces over your base space X. This gives you an induced fibration of adjointable operators. And so you can apply techniques for Hilbert spaces and bounded operators at the level of fibers. You then need a clever lifting argument to be able to build this up to give results actually about adjointable operators. That's the technical difficulty here. But actually this technical difficulty was solved in the case of W star bundles as part of the technical machinery in Ozawa's paper, and a lot of his results do generalize to this broader concept of strictly closed subalgebras which contain all scalars, so all C of X functions. Okay, so to close, I just wanted to tell you a bit more to sort of close the loop with the example here. What you can show in this case here, so when you do have the special case, so assume that at the level of fibers you now have a subfactor, so you can define index, so that's for all X, and you find this behavior is sort of typical, so you can show that this index is automatically lower semi-continuous. Yes, this follows from one of the estimates due to Pimsner and Popper for the index of a subfactor. So you choose the one that's in terms of 2 norm, because the 2 norm is the stuff that we can control in W star bundles. And actually the continuity of this index is precisely what we need to define let's say a C of X trace on this basic construction here. And once we can do this, it turns out we can also get the whole of the Jones tower to work in this context. Running out of time, so I can't give the example here, but one thing you can do here is you can also put an example where you can actually realize this, so you can actually give an example where, so here's an example where you essentially take Jones projections. How do you do that? That's the best way to say. So the way you get an example over M where each fiber, so the base space X is some subset of allowed Jones indices, and you can get that this N in M is the subfactor, so R lambda. So this is a subfactor where you take Jones projections, you look at the view R as the von Neumann algebra generated by all the Jones projections, and R lambda is the subalgebra generated by all except the first one. And so you can do this in a continuous way over a space, and you get a subfactor, a sub von Neumann, a sub W star bundle where each fiber has these things. This is an example of a natural family of subfactors which can be realized as a W star subbundle. But on that, I think I'll close. Thank you.
Are there any more questions or comments? I still don't see why you need the X to be compact.
We can talk about that one
Okay.
a bit later.
Okay.
Thank you, George.
We resume at 4 o'clock.